third in a series of webinars on RF on behalf of the HCM Electronics Roadmap and on behalf of Holland High Tech. My name is Simon van den Berg from Thales, Netherlands. I'm standing in for Hans Naus, who is unfortunately unable to fulfill this role at the moment. Anna, if you could put the next slide on, please. Anna, can you put the next slide on? Okay, thank you. So this is the third in a series of webinars on RF. The first one was done by Jo on the development evolution of microwave technology. And last December, we had a talk by Frank van Vliet of TNO on microwave applications for radar. And today we are happy to have Cicero Vaucher from NXP over to give a talk on RF applications for automotive radar. On the next slide. So a couple of things before we start. We aim to record this session. So if you would not want to be on the recording, please switch off your video feed. We will make the link for the recording available for the attendants later on, so you can look back and look at parts of the presentation at your own pace, at your leisure. Further, some household things. We would prefer to have all the questions at the end of the session. There's a Q&A time for that. If you have any questions, please post them in the chat, or if you don't want to do that, keep them available for later. And later on in the Q&A, if you have a question, please use the raise hand to indicate that you have the question. Anna will collect we'll monitor the chat so we can see your questions in advance. All right, so next slide, looking at the program, I will say a few words on the HTSM electronics roadmap, what it is about, and what we are doing there. And then you will have the presentation by Cicero on the latest generation of automotive radars, covering a range of topics from waveforms to system implementation and the underlying technology. And around 4:20, we have a Q&A where everybody can pose their questions. And we aim to end around 4:30. So going to the opening remarks on the HTSM electronics roadmap. The next slide. Okay, so just to briefly, in a couple of slides, take the scope and the purpose of the HTSM electronics roadmap. HTSM electronics is one of the roadmaps in the high-tech systems and materials domain. And basically our roadmap aims to join together all the entities doing work connected to electronics. So going from industry to universities, knowledge institutions, SMEs, as long as it's about chip technology or component technology or packaging or anything associated to that, that is what we aim to cover. And we aim to connect those companies and to support all the R&D activities in Holland as best as we can. And the electronics roadmap is basically underlying for various other roadmaps. And it supports the various knowledge and innovation themes and key technologies in Holland. Next slide. So in let's say as a bird's eye view of what would we cover, and the scope is very broad, so I'm not even aiming to be very complete here. You see the various topics and technologies that are covered by the HTSM electronics roadmap, and also by the companies and institutions that are in that roadmap. And I have highlighted some of the topics that touch upon today's talk by Cicero. And you can see it's quite wide-ranging, going from analog, active to passive, power electronics, actuators and sensors up to almost system level, and from analog to digital. So again, it's quite good. If you are interested to hear more about this, there are 2 mail addresses at the end of the presentation, so please don't hesitate to contact either Hans Naus or myself if you're curious and if you have any questions on this. All right, so next slide. Okay, so basically to take away HDSM electronics, it's an enabling roadmap. We cover a lot of anything really touching upon electronics and components. And basically our slogan is there's never an end to more. There's always more than more. And let's invest and challenge ourselves to further that electronics roadmap. So next slide. This was very shortly on the HDSM from my side. Then I would like to introduce Cicero Vaucher from NXP and also Delft University of Technology. So Cicero, we are very happy that you could make time and that you're willing to show us the latest on automotive radar. Cicero has quite a long history in this field. He joined Philips and then went to NXP, and he is now the authority on automotive radar and topics associated to that, such as signal generation and waveforms. Numerous qualifications on this, as you can see. And apart from his position at NXP, he is also part-time professor at Delft University of Technology on millimetric wave radar. So Cicero, once again, thank you very much that you were willing and able to join us, and the floor is yours.
Yeah, thank you, Simon. Thank you very much. And let me share my screen. Okay, yeah, thanks, and welcome everybody. And yeah, it's my pleasure to be able to walk you through a set of slides on yeah, automotive radar and associated automotive markets. And to start with, let me check, yeah, that one. So at NXP, yeah, automotive plays a major role in our product portfolio, and we can group basically into along three axes: the axis of autonomy, electrification, and service orientation. And yes, as of today, the topic of our talk is about autonomy and towards zero road accidents. So, and to see what the impact of technology is in safety, this slide shows us as a function of time, starting in 1950, the number of fatalities in the Netherlands, and then we could see that it went very steeply up until introduction of safety belt, and then it starts decreasing, and we see that a number of other technologies such as ABS, airbags, and stability control, they steadily help to decrease the number of fatalities, but yeah, still there is yeah, quite a way to go. And as of today, there are more than 1 million fatal accidents a year worldwide, and yeah, that's quite some extremely high number, of course, and that's why this technology is also very promising to work on, basically active safety. But yeah, active safety and automated driving, this is not going in a single step. So the industry already around 10 years ago, they defined roughly a number of levels that we could basically qualify from the basic level of driver assistances towards higher automation. And And here the main difference is when drivers, the driver responsibility or the vehicle is responsible for safe operation. So I think there is some noise on the line. If you could mute, that would be welcome, please. Thank you. So the main point here is that we can also see, for example, who is responsible for safe operation, and we can also say that who has control of steering and who has control of the vehicle speed and control of complete vehicle at the end. And we see a basic level 1, for example, the vehicle is only doing velocity control or maybe a bit of steering, for example, for lane keeping, but most of the responsibilities is with the driver. And yeah, as we move up, then the vehicle becomes more and more taking care of controlling the, but still you see that up to level 3, the responsibility is still with the driver, even if the vehicle could in principle be taken full control of where it's going. And finally, level 4, high automation, and 5, which is not shown here, means that the driver is fully not in control anymore, but also not responsible. And the vehicle is then also taking full responsibility for, and also liability. So this is, a gradual evolution. It's not a revolution. And it's also interesting to look, I made here, I searched for the hype cycle. And this is the one then for 2022. And if we would look back 5 years ago, 6 years ago in 2016, then autonomous vehicles, they were really at the top of the peak of inflated expectations. And everybody was talking about autonomy, and we are there. But yeah, it was not exactly like that, because actually there were a number of fatal accidents that cooled down a bit that animal. And now, yeah, 6 years later, we are, let's say, at the bottom of the hype, which in itself is not a bad thing. And we are now ready to go to really quality of service. And I made a scan of recent news that Waymo is now offering driverless services in San Francisco. This is from 3 weeks ago. This one was funny, that a self-driving car was stopped by police in San Francisco. And even yesterday there was some news from the UK that they are planning to basically make watch films allowable on the motorway. And then the insurance companies would be liable for accidents. So I have my doubts if this is going to fly, but you see that even in the background there is quite some activity going on related to autonomous driving. But I would say very important was also this piece of news from also about a month ago, that Mercedes will be legally responsible while their drive pilot system is engaged. And that means, of course, that that's one of the major pieces of the puzzle, is who is liable in case of an accident. And now Mercedes is coming and saying, if you have our car, you are not liable. Of course, this is still not the whole story. It's up to a maximum speed of 40 miles per hour. And there is also 10 seconds notification that if the system has to disengage, there would be a 10 seconds period where it would call the attention of the driver, such that the driver has then time to take over responsibility for the vehicle. But it is the first time that any OEM is saying we are responsible for a vehicle while in autonomous mode. And as this writer says, yeah, this is really the first day of school and Mercedes is the teacher. Yeah, it's an interesting view on this development. Yeah, this of course is the top model of Mercedes, I think an S class, and you also see quite a number of sensors that are needed to create such. This would be basically a level 3 car in autonomy. So yeah, that's nice. It's a good development, and we see. I expect that let's say in the next 5 to 10 years that basically this will come, and then again we will not be surprised anymore, and it will become part of our lives, but gradually and not as in one day to another, as we might have thought 10 years ago. So let's look now into the sensors themselves. So we see that for autonomy, these cars really need not a single sensor. You really need a number of them, and they are quite complementary. And we might say start with the camera, because the camera is very good in detecting the pattern and colors, for example, of a traffic light, for example. At the same time, a camera is very sensitive to rain, but also for the sun. And yeah, it would not work at night, so it's a good function, but yeah, also very sensitive to the environment. Radar, on the other hand, is very good at measuring speed and distance to another object, and is relatively insensitive to environmental conditions. And finally, we have LiDAR sensors, which are then very good to measure angular or have very high angular resolution, as well as measuring distance, but also LiDARs are affected by rain and snow. So yeah, what we see now is that yeah, you see these more expensive cars, they do have all 3 sensors, whereas the more entry-level cars, for sure they have radar and camera combined, and this is actually reflected on also on this slide, where we see that 60% of new vehicles next year will be partly automated and contain radar. So that means, yeah, 40% of all cars will have can be categorized as level 1, 15% as level 2. And here also you see you have more radars as well as more modes of operation. Level 3, yeah, this is still coming slowly, but already coming, which was the case of Mercedes. And finally, yeah, the real Waymo full automation, will be still less than 1%. But yeah, as I said, I expect in the next 5 to 10 years that this will also become more significant. What we see here is the number of radars and the number of cameras as a function of the for these classifications, and you see that even an entry-level car already has probably 3 radars, whereas as you move up, this increases quite quickly. And now looking more into the radar themselves, for these radar sensors, what are the fundamental requirements that an OEM would like to see? First of all, you want to have a compact size. You want to have the performance and not take a lot of space behind the bumper, for example. From the perspective of integration, you want to have a scalable concept where you might have then one chip that you can use on the for different use cases. And the different use cases can roughly be categorized here. So flexible field of view, basically you don't want a radar which is very narrow band, you also want to have it broader. You should be able to measure azimuth as well as elevation. and ideally to have a high angular resolution approaching the performance of the LiDAR, which stays a very expensive sensor. You want it to be relatively immune to interference. We expect that in the near future, as the interference would become more of an issue or a challenge, and therefore you need to keep that into account while designing the system. And yet, lower power is also quite important. So you, especially when you go towards electrification, and if you have several of these radars in a car, then each of these radars, you should minimize the power. And nowadays we speak around 4 watts for a complete sensor. So in terms of waveform, what type of waveforms are used in automotive radar? And presently we see the so-called FAST-CHIRP-SEQUENCE being used. And the fundamental property of this waveform is that you have a number of pulses which are basically frequency modulated. So this is the frequency of the pulse, and they are linearly modulated as a function of time. And then the period of the modulation is around between 10 and 40 microseconds. That's why it's called the fast chirp. So it's around this order of magnitude for each chirp. And basically the principle of operation is very powerful, because if you consider, for example, the blue one is the transmitted waveform, the red one is the reflected waveform. When you look at the reflected waveform compared to the transmit waveform, and you compare the phase of those signals, if there is a relative difference in velocity between the cars, the phase will basically change from pulse to pulse. And this is then given as a direct indication of the relative velocity between these objects. And that in itself is quite a powerful technique, because you don't have the so-called range velocity ambiguity that the previous waveform had, which was with the slow chirp, one chirp up and down, and that created some type of ambiguities in the detection. And second, if you use this waveform, you are not limited to any number of targets. In principle, you can have a very large number, and you don't mistake them on the base of range and velocity. So how do we map this into a processor? So basically every chirp, when it's returned, we digitize the IF frequency in the mixer, and we do the so-called range FFT. And what we see here is the number of chirps, the chirp sequences moving along the y-axis, and this zeta-axis is the different antennas, for example, that you might have in the radar. So for every chirp, we perform a range FFT, and then we arrange the output of the FFTs along the so-called range gates, and we build the so-called data cube. And after we complete the chirp sequence, then the range gates are fully completed here, so the cube is full. And then there is a second FFT along the range axis. And that is basically where the phase on each range axis is compared to each other, and gives an indication then of whether there is a relative movement or not. And in this case here, we see then one example, which is then a 2D plot, and it represents then 3 different targets in different positions and velocities. But I have some more realistic examples coming up. And And basically, one of the enablers for this fast chirp sequence is, of course, signal processing. And as with the scaling of technology around 12 years ago, Freescale came with the first integrated processor for this type of fast chirp sequences. It was already supported by the existing technology. The other side of the question is, if you have this processing, can you also do the millimeter wave part of the radar, which is basically the high frequency part? And for that, we already made some experiments early on, for example, with a 60 gigahertz LNA, where we had quite a good noise figure around 3 dB at that time. This was 40 nanometers. And we also created some mixer down converters, passive mixers and LNAs. And here we were able then to compare that, yes, indeed, we had a decent noise figure comparable to basically to bipolar implementation at that time. And also we were able to meet a very high input compression of around, in this case, 4.8 dBm for the mixer. So yeah, this was the basic elements in order to know, we are able to build a radar front end with CMOS technology in 40 nanometers. Another aspect of CMOS technology that's actually beneficial for automotive radar is the thermal behavior. So we see that normally a CMOS transistor has a distributed nature, where that means basically there is a very large contact from the active area towards the substrate. And by means of thermal simulations, we were then also able to assess that we would not expect a very large difference between the hotspots in the circuit compared to the substrate. And in this case, it is a simulation of a 3 transmitters system. So here we see then the transmitters and the PAs. So the power amplifiers are visible, basically, the output stages. But if we look at the difference between that hotspot and the coldest part is not more than 7 degrees, basically. And that was actually quite also so some good insights that actually CMOS was not as bad as some people might expect from the thermal management perspective. And I think finally, even more important than the previous items is that CMOS is ideally suited for high complexity mixed signal functions. And there are, of course, 2 fundamental functions for this type of radar, and one of them is the chirp generator itself. So we have seen we need to create those fast chirps in a very short interval, and this is ideally mapped into technology like CMOS, and these are real measurements where we do a 4 gigahertz chirp. So that's from 77 to 81 gigahertz, and the period is 16.8 microseconds. So, and another key element are the ADCs, so the analog to digital converters. And in radar, we have to deal with very high dynamic range. So objects that are close to the sensor can be very large, and objects that are far away, are very small, they're very weak. And here we see, for example, one of the ADCs used in our product where we have 100 dB, more than 100 dB dynamic range, from 0 to minus 100 dB full scale. And that's basically what you need to have as well. So we, as at NXP, we have already, we put this together, and we are now close to releasing the second generation, and the third generation is also well proceeding. So the second generation in 40 nanometers, we have here then a functional diagram where we have 4 receiver, 4 ADCs. So it's a full receiver path. Here the programmable decimation filters and the serializer. So basically here we have a digital interface to the processor. And on the transmit side we have 3 transmitters, programmable phase rotators, and the waveform generator. Expansion interface allows to combine multiple of these ICs together to create a distributed system. So I'll come tell you more about that in a moment. And all of this is basically integrated in a small package with 7.5 by 7.5 millimeters. And this product has actually a so-called exposed die. So here we are looking at the back side of the substrate, and this also allows them very good thermal connectivity to, for example, for a heat shield. So this is then the downside and the upper side. Here are some examples. So if you have such a chip, basically you have all the functionality that you need to create the function, the millimeter wave as well as the mixed signal function. You only need a crystal of 40 megahertz, which is, here is on the back side. You cannot see it. Here is another board where we demonstrate. You can see the crystal on this side. And other than that are only some passive components for decoupling of the supply lines. So if we would test such a system, and we saw, I told you about those 2D plots, and normally they would look like this. So here we can plot the relative velocity and the distance from the sensor. And in this case, we were testing on a parking lot and with different chirp bandwidth. So if we would measure with 300 megahertz chirp, then this is how a car at 80 meters would look like. And when we measure with wider bandwidth, for example, 1 gigahertz, then we can see that the car is also showing along the range. So you see some properties of the car. And here I have a pedestrian, and I think if it works, so a measurement also with a colleague walking away from the sensor. So we can basically see the so-called micro Doppler. So see if we can see it one more time. It's a bit complicated. So what we see is basically the movement of the legs and the arms along the velocity axis and moving away, and then we get this interesting response. And this is simply the outcome of the second FFT. There is nothing really post-processing yet here. That's basically just a sequence of FFTs being performed. Another aspect which is quite important is how that sensor would behave behind the bumper. So this is a kind of a famous challenge in the automotive industry. What happens, how does it behave? And in this case, we had basically a bumper or a piece of a bumper with metallic paint in silver, which is some type of worst case from the reflectivity perspective. So we made some measurements. So we have a corner radar at 1.5 meters from the radar, and we can measure the bumper in 2 different distances. And the outcome of this experiment is shown here. So we see, for example, that when in blue, we have no bumper, so that gives us the reference also for the reflected power from the target at 1.5 meters. And what's important here is that when we do place the bumper, which is either at closest or very close to the radar sensor or at 3.5 centimeters, we see that in both conditions there is no influence on the noise floor, but there is some influence on the transmittivity of the basically the wave gets a little bit attenuated because you go 2 times through the bumper, and this is something fundamental. You cannot really deal with the insertion loss of the bumper, but what's really important from the perspective of the radar is that the bumper itself will not lead to an increase of the noise floor, or basically decrease the effective noise figure. And this was basically reached with our design. And what that means is that the amplitude noise on the transmitter is low enough that when we have a stronger reflection, that would still not change the effective noise figure of the sensor. So yeah, that's wanted to share with you. Now let's look at angular resolution. So yeah, before we have discussed about the LiDAR and how LiDAR is basically complementary to radar and cameras, but it's also the most expensive sensor. And yeah, how would it look like if a radar could also reach that type of angular resolution, which is sub 1 degree? That's very high and also very difficult to reach. But yeah, you need to start somewhere. And we started basically with a so-called MIMO antenna array configuration. And this is then a specific test board, a test PCB, where we place the receiver antennas at a distance of lambda over 2 from each other, and this is actually done to avoid grating lobes in the angular response. And the transmitters, they are placed at a certain distance of 2 lambda from each other. And here the trick is that if there is some angular azimuth difference, azimuth direction, which is not 0, basically we can increase the size by creating so-called virtual array of 12 antennas. In mathematical terms, you would create a convolution of those elements. And what we see in practice is that sometimes these receiver antennas, they are also not placed exactly at lambda over 2, but they could also be placed further away when people are able to deal then with the grating lobes, for example. That's also possible. So these are not, these are simply complementary techniques that can be used and are also used in practice. And basically here was then a test of concept, a proof of concept. So we have our chip with 3 transmitters and 4 receivers. So we have an angular resolution of 70 degrees times lambda 0 over aperture. So that's diffraction limit. So if we would not use the MIMO and we have this small receiver array, so we only have around 35 degrees, which is, is quite very low resolution. When you use basically the 3 times MIMO, then we are already down to 12 degrees with the virtual arrays. And this is then, here we made then some measurements, and we see then, that actually we have a very nice measure, very well matching the theoretical resolution prediction. And and if you are at 12 degrees, of course, it's still quite high compared to the LiDAR. You would like to go closer to 1 degree resolution. And how you do that? Basically, this is one example of how this can be accomplished. Basically, here we see a cascaded radar, where we have then a cascade of 4 chips. You see the receiver antennas on this side, the transmit antennas on this side, and we have then one additional chip in this case that creates the LO signal. And what's important here is that for this distributed array to work, you need to have the LO to be coherent on the different dies, as well as the ADC sampling must be coherent. And then basically you are able to use multiple dies in a cascaded configuration, and also the sampling of the signals is also consistent in the way you need to get your good angular estimation. We have done, so basically this is our first generation of RFCMOS. So in this generation, we do not have possibility to use the same die to generate the LO and use the LO with the delay going through the PCB. So we had this configuration. Our second generation has the full cascading capability, and then you only need 4 dies, and then you already have then the full capability of the array. You don't need the extra die to create the LO signal. And this is one of our latest work on cascaded radars, as well as imaging radar, basically. So here you see the 4 dies. In this case, they have the exposed backside, and we have used then the waveguide, and the antennas are printed. It's a different setup compared to the previous slide, but yeah, the principles are very similar. But yeah, of course, if you are using these different antennas and you're saying, yeah, how can I avoid that the antennas are not interfering to each other, even if they are my own antennas? So yeah, that brings a set of challenges. And yeah, the most elementary way of doing such a MIMO configuration would be to use sequential switching of the first antenna, the second, and the third transmit, and then you repeated it. But yeah, in practice, this is not working very well in automotive radar because of the moving conditions of the environment. And then we only have one transmitter, which is actually hurting a bit in the link budget, because if you have multiple transmitters, you could also profit from higher transmitted power. So we see now, a combination of investigation, research into new waveforms, where, how can you use basically those antennas simultaneously? And for example, very common today is to use so-called Doppler division, where you have code for different antennas from chirp to chirp. And if you want to do more sophisticated things, such as the frequency division, then it becomes actually kind of difficult, and you need to do with spillover challenges, so-called in the receiver path. Going further, we are looking at code division, and code division means that you can use different codes or random codes from chirp to chirp, as well as inside the chirp itself. But this is also a step further, and here also we have to deal with some challenges, such as spillover cancellation. This is going to be addressed. So the waveform evolution, if we start with where we are today, is a relatively simple implementation. You know, we have the chirp generator, the phase locked loop, creates the chirps, the chirp sequence. We have the transmitter with the phase rotator control and the receiver, and this is relatively straightforward. If we want to say I want to do modulation while I'm chirping, for example, then basically we need to have a modulator on the transmitter ports. And that's basically something that we are also working on at the moment. So then basically we can modulate the transmitter also while chirping. Yeah, that in itself has a number of challenges. Yeah, so the waveform design itself, this is still quite a field of study. How to improve the FAST-CHIRP-SEQUENCE, that's not yet properly established. But we do know that if we start modulating the chirp itself, that there is a bandwidth expansion, so we need to increase our baseband and also the sampling speed of the converters, for example, from 20 megahertz today to 200 megahertz, perhaps to even 2 gigahertz in the near future, while still maintaining the noise figure in the lower phase noise. And also, yeah, how to deal with the echoes that you have, full duplex, when it to have the crosstalk from transmit to receive. We are also looking into launchers in the package, such that we don't need to have these PCBs, expensive PCBs anymore. You go direct from the package into the antenna network. And all of this, obviously, you need to do while maintaining a high power efficiency. And that could mean that for the future, we might also migrate to another technology node that might give us a higher power efficiency in our, especially in the transmitter path. Synchronization at millimeter wave, how if you have like this number of ICs in different locations, this is still something which is power hungry when we need to distribute the low signal along the PCBs, and the LO is normally around 38 gigahertz, for example. Can we do this better? That's something that we are looking at. And of course, we always have the challenge of lowering the phase noise of our integrated synthesizers. Yeah, this slide summarizes the challenges that we need to deal with, or we are working on. Still, I would like to come to the conclusion with a statement that we have come a long way compared to 10 years ago. 10 years ago, nobody would say CMOS would really be dominating the market in 2020 time frame, but yes, that became a reality. And we have been able to have a scalable concept. Here we have one chip corner radar, long range radar, and here an imaging radar with 4 of the same dies. And that we believe is a very powerful concept. Yes. So in conclusion, so we have seen that CMOS give us almost everything we need to, and that maps into a waveform designs for FM radar, automotive radar. So we have room to improve the performance at 77 to 81 gigahertz, but we also have new challenges. And we need to address them with antenna array, transceiver design, as well as waveform designs. And automotive radar is here to stay, and it's increasing safety, and it's also saving lives. And it's also good to see that we are out of the inflated expectation phase in the hype curve and going towards the plateau of productivity. Yeah, that concludes my talk. Thank you.
Well, thank you very much, Cicero. Was quite a fascinating overview and insight into what is going on in automotive. I must say I recognize quite a bit of your challenges from my own domain, so that it's very interesting to see, and also interesting to see what the differences are in that. Well, the floor is open to questions. So if you have any questions, please raise your hand or type it in the chat. Are there any questions at the moment for Cicero? Yeah. Go ahead. I see one person with a very difficult name that I'm not even going to try to pronounce, but go ahead.
Yes, no problem. Hi, Vaucher speaking. Cicero, thanks a lot for a nice presentation. I actually have two questions. One is when you show this actually a radar solution when you have multiple ICs, right? And first you distributed the LO from one PLL, but then in the second generation you said that every chip will have its own LO generation. Then I have a question for the second case. How you make sure that the phases of PLL are the same?
Well, it was not exactly what I said. What I said was that the chip which is producing the LO is able to use the LO coming back from the PCB, and that means that the phase we go out of the master, so-called I should say the leader today. The leader produces the chirp, it goes out, and then there's a star division, and then it comes back also to the leader as well as to the followers, and then we keep an equal time delay on the PCB. And that's,
okay.
And you are right. For the situation that you mentioned, we are still working on it. We don't yet have a solution.
Okay. Because in the first case, you just need to manage in principle delay, and you can do that, let's say by in the layout or by some circuitry controlling the delay. But in the second case, it's more difficult when all let's say chips have their own PLLs, right?
Yeah. If you have your own PLLs, then there are other problems also.
Yes. Okay, but you are still working on that.
Yeah, for sure, absolutely. Yeah.
Okay, and the second question is, let's say in this last slide, you mentioned plenty of room on 70 gigahertz, 70 to 80. What do you think about 150? Because we start working and there is a lot of activity on 150 gigahertz, majorly, let's say, a lot of bandwidth. How do you see this, let's say, 150 gigahertz band for the radar? Do you see that as appealing, or you can say there are many more problems than advantages? How do you see that?
Honestly speaking, speaking from the perspective of a product architect, today it would be a little bit far off in the future. On the other hand, of course, more bandwidth is always better. Yeah, how this band of between 140 and 150, how this will materialize in the future is something which is still open. But for sure, what is very important is always regulation. So one thing is what's possible, another thing is what does the regulation allows you to do, and then we need for this type of industry to have some type of harmonization worldwide, which normally takes a lot of time to be reached, basically. So I think 140 gigahertz would be, yeah, it would be very appealing to work on. So I'm glad to hear you are doing that.
Okay. Thank you. That's all from my side. Thanks.
Okay, thank you. Are there any other questions at the moment? If not, I would like to take the opportunity to ask a question of my own. I have a background, I come originally from the antenna domain, so when you talk about side lobes and so on and sparse arrays, I always get interested. Cicero, could you indicate at all what kind of side lobe level are you talking about? Is it possible to give to put a little bit of a bandwidth of numbers on that? And how important is that for you in your application?
It's a bit difficult to say up front. What we see in practice is that the tier ones, they use this as a design freedom, basically. So it's a trade-off of angular resolution and design freedom. And then it depends very much on the field of view of the radar, like of the intended application, whether it would become a problem or not. It's difficult to say up front. You see from the perspective of NXP, we will support with one design a very large variety of applications. This was the most important from our perspective. At least, yeah.
Okay, that's clear. The reason I asked is because for our applications, the side lobe level of the system is very important, and we take a lot of we put a lot of effort into lowering that both on the antenna side and on the RF electronic side. So I was curious to see how that comes back into your domain. But thank you, Cicero.
Yeah, for example, normally we don't do amplitude tapering. The customers are not yet using analog beam steering, for example, as I think you do that, right? I think that's a key element of your antenna array. And in the automotive radar is more like you want to get a very wide illumination of the environment with the transmitters, and then you do the analog processing in the digital domain. And I think there's a bit different way of doing it.
Yeah, correct.
Yeah.
Okay, looking at the time, I think we have time for a last question. If there is anyone who has one, feel free to ask. Well, it seems there are no questions. I think we are also at the end of the allotted time slot. Cicero, rest me to thank you very much again for your excellent presentation and your contribution. Much appreciated. Just to reiterate, for those who have been attending, there will be a link distributed where you can watch the presentation again. It has been recorded. And finally, from my side, we will be continuing our webinar series, and we're currently working on a series of presentations on flexible electronics. So stay tuned for news on that side. So Cicero, thank you very much again. Anna for organizing, and all the participants for your input and your listening. Thank you very much.
Thank you.
You're welcome.
Thank you.